All right, welcome back. Let us pick up where we left off, and then we'll also go through some new slides as well today, so you can get to your essay. So we're talking about logic gates, cool stuff that you can do with them, with true and false, and it just so happens that it's very closely related to this concept called binary, which you may have heard of. Okay, so let's talk about that now, and maybe you've heard about the whole ones and zeros thing. Well, now you're ready to make numbers using just ones and zeros, okay? We're going to learn the binary number system. So the idea is true is 1 and 0 is false, and just everything in our computer is nothing but logic gates, okay? So our computers are just made up entirely of these guys, and if 1 is true and 0 is false, all the information, therefore, that's in our computers, this presentation, my voice that's coming to you through the internet, it's also just a bunch of ones and zeros, which is weird to think about. So let's talk about how to store stuff, how to represent anything at all with binary numbers. All right? So let's get started. So binary is just a number system, and you are probably much more familiar with base 10, which is also known as decimal. Okay? And the reason we call it base 10 is because you have 10 digits to choose from when you're making numbers. 0, 1, 2, all the way down to 9, which is 10 digits in total. That's where we get the 10 and base 10 from. Okay, so we think that we came up with the base 10 number system because we have 10 fingers on both of our hands. So we got that times 2, right? So maybe in the Simpsons world, they would be counting in base 8 for that reason. So that's decimal, and now that I've told you all this stuff and spelled it out, binary is going to make a whole lot of sense. So binary is just base 2, okay? It has 2 digits to choose from to make all of its numbers. You have only 0 and 1, 2 in total. So when you're in decimal and you add 1 to 9, your last possible digit, you have to make a new place, right? You have to go to 10. That's the next number. We didn't have enough digits to stay in the ones place, yeah? So a similar thing happens in binary. So you count from 0 to 1, and then you try to add 1 to 1. Well, you don't have enough room to stay in the ones place in binary. So the next number, 2 in binary, has to be 1, 0. You have to carry. You see that? That's weird to think about, and we'll talk about the conversion in just a second. Let's introduce a little bit more terminology, because you might have heard of this as well. So a bit it's a 0 or a 1, it's a binary digit, okay? That's why they call it a bit. Maybe I should put it right here. And the reason they call it bit is because they took this letter here and these 2 letters here and just squished them together. All right? So here is a 4-bit number. Okay, 1010, and we'll talk about how to figure out what that even means in just a little bit. And then finally, a byte is an 8-bit binary number, and you've probably heard the word byte before, like megabyte, gigabyte, things like that. So it's just 8 bits. That's all a byte is. So here's 1010, I don't know, 1001. That is an 8-byte number. That's 1 byte. Okay? And it gets very confusing when I'm writing both decimal numbers and binary numbers, because they can look the same. So what we do in computer science or any math class that's talking about different bases is we put subscripts after them to talk about which base we're in. So this means I'm in base 2. Interpret this number as a base 2 number, not like 101 million, all that stuff. Okay, it's a different number. So for instance, 1010 in decimal is a whole lot different to 1010 in binary. Okay, this is like 1,000. This is much less than 1,000, and we'll talk about that soon. Okay, so hopefully this is all making sense. This is binary. You are now introduced to it. So let's talk about how to convert now. So we would like to be able to go from binary to decimal. Okay, back to the number system we know and love, so we can actually reason about these numbers. So remember that we're going to use these subscripts now to talk about whether or not a number is in a certain base. And so the question is, okay, if I have this number, what in the world is it in binary? Or what in the world is it in decimal if this is a binary number? And the secret is to remember our elementary school math where we're trying to break down numbers into their places, yeah? So this is like the thousands place, this is the hundreds place, this is the tens place, this is the ones place. If you break it down, eventually you can come to these little statements here. So it's 1 times 1,000, 2 times 100, 3 times 10, and 4 times 1, yeah? So it just so happens that this works exactly the same for binary. You just replace the base, yeah? So instead of 10s everywhere, it's 2s everywhere, okay? So that's the key, and you work from right to left as usual. So this is 0 times 2 to the 0. I'll write this way over here. 0 times 2 to the 0, plus, this is 1 times 2 to the 1. Okay, that's how you convert. Plus 0 times 2 to the 2, plus 0 times 2 to the 3, plus 1 times 2 to the 4. So that's what this number is. We just have to finish this off and we'll know exactly which number it was. So this is 1 times 2, 4, 8, 16 plus 2. So that makes it 18 in decimal. And oops, I had a little typo here. This is just saying all this over again, just getting rid of all the zeros everywhere. So this is 16 in base 10 plus 2 in decimal. That's 18 in decimal, yeah? So that's the idea. So yeah, you just use this kind of expansion idea and you do your math in decimal that you already know how to do. So maybe take a second to try this one and then I'll show you the answer. Okay, assuming you're back. Well, this is just 1 times 2 to the 0 plus 1 times 2 to the 1 plus 1 times 2 squared plus 1 times 2, that's a 2, 2 cubed, which is 8 plus 4 plus 2 plus 1, 8 base 10, of course, plus 4 base 10 plus 2 plus 1, which is 15 base 10. Okay? That's the biggest 4-bit number you can have. Okay? So that's that. And, well, that is the easy way. The other way is a bit harder, and I'm sorry. It requires you to take remainders repeatedly and also do division. Okay, so let me maybe show you how, and then we'll go from there. How to do it in decimal, that is. So if I have this number in decimal, how do I get the numbers, these individual digits out of it? Like I want the 3 out of 123. I want the 2. I want just the 1. How can I use math to do that? And the secret is, well, you can actually get the rightmost digit by dividing by 10 and getting the remainder. So if you divide 123 by 10, you're gonna get 12. 12 remainder 3. Okay, so that's the idea. So that's how you can get the rightmost digit. And to get the rest, to get the 2 and the 1, you can play the same game. You can just turn 123 into 12, like get rid of this 3. So then you can do the same thing, get the rightmost digit on the 2. Okay, it's a weird little process, but that's how it works. So how do you convert this to this? Well, it's just the division part, forgetting the remainder after dividing by 10. Isn't that cool? So yeah, you just remember this part, and so now you can use 12 to get the rightmost digit when dividing by 10, because now it's 1, remainder 2. So I got the 2. And now you can use the 1. 1 divided by 10. Well, that's 0, remainder 1. So there's your 1, 2, 3. Yeah? So, and then once you hit 0 over here, you're done. Okay? So that is the algorithm. That's the sequence of steps to do this. It's a bit weird of a process, but you will get it. All right, so let's try it for a certain number in binary, because this works in binary. So we were doing stuff in base 10, so we were dividing by base 10, taking remainders and things. this works regardless of the base. Okay, we kind of like, just like we took 123 and we shifted away the 3, we can take a decimal number and shift away the binary rightmost digit. I know that's a bit weird to think about, but that's why I'm teaching it to you. Okay, so here is the algorithm for converting decimal to binary. You're going to repeatedly extract the rightmost binary digit, so yeah, rightmost digit in binary, I guess, by taking remainder after dividing by 2. That's what this sign means. It's called modulo. Okay? Whee! So think of it as remainder. Remainder when dividing by. Okay, that's what that symbol means. And then we're going to shift away that bit that we just found by dividing by 2 and forgetting the remainder. Okay? This is called integer dividing by 2. Forgetting the decimal places, forgetting the remainder. Okay, so that's the secret. And, well, let's do this. Let me convert 8 base 10 to something in binary. We don't know what yet, but we're going to figure it out. Okay, so we start with 8, and we're going to keep on doing remainders, or keep on dividing by the base and getting the remainder. Okay, and then shifting away by dividing by 10. Okay, or dividing by 2, sorry. So here is the 8, and I'm going to get the remainder after dividing by 2. That's the first thing that I'm going to do. Okay, and this is an even number, so 2 goes in cleanly, and the answer is 0. So that's the remainder when dividing by 2. That's just 0. And then I'm going to shift away the 0 that we just found. That's the rightmost digit in the binary number, which is fun to think about. Then I'm going to divide 8 by 2 and drop any remainders that exist. There are no remainders, so that's nice. So this is just 4. And so now I'm going to work with 4, and I'm going to try and convert that to binary. Okay, and every time I take a remainder, take a modulo operation, I get a digit. Okay, so now I'm going to work with 4. 4 mod 2, and I shorten modulo to just mod. We say that in math. 4 mod 2, again, it's an even number, so it's 0. 4 divide by 2, drop remainders, that's 2. 2 mod 2, again, it's an even number, 0. 2 divide by 2, drop remainders, that's 1. 1 mod 2, ooh, okay. That is finally 1, because it doesn't go in cleanly, and then, if I write this really tiny, sorry, 1 divided by 2, dropping remainders, that's 0. Okay, so 0 tells us we can stop, we're done. And then every time we took a remainder, took a modulo operation, we found a digit. And we got them in reverse order, if you remember this over here. It was the 3, then the 2, then the 1. So here we go. That means the answer is 1, 0, 0, 0 in binary. And you can always convert it back to decimal to confirm this. This is the 1's place, 2's, 4's, 8's place. Yes, it is 8. Cool. Okay, let's do a harder one. 25 mod. 25 base 10. Convert that to a binary number, please. So maybe you give this a try yourself, and then we'll do it on the next slide. Okay, so 25 base 10. What is it in binary? Base 2. Well, we're going to repeatedly take remainders and divide by the base we're trying to convert to. Okay, so this works for other bases like base 3, if that was a thing, if you wanted to use that. So this is binary. So 25 mod 2, well, that's an odd number, so it's going to be 1. Okay, 25 divide by 2 and drop any remainders, drop any decimal places. It's 12.5, right? So it's just 12. Okay, and we're going to keep playing this game with 12 now. 12 mod 2, that's even, so 0. 12 divide by 2 is 6, then 6 mod 2, even again, so 0. 6 divided by 2 is 3. 3 mod 2, that's odd, so it's 1. 3 divided by 2, it goes in 1 time, it's 1.5 when you drop the remainder. 1 mod 2, well, that's again odd, so it's 1. And then 1 divided by 2, dropping remainders, 0, and we're done. So every time we took a remainder, we got a digit. Boop, 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 and boop. Okay, so that's the answer. It's, well, it is, I'm going to read it off backwards, remember. So it's 1, 1, 0, 0, 1, base 2. That's what 25 is. Okay, we can confirm this by figuring out which, by converting this back to decimal. This is the 1's place, the 2's place, the 4's place, the 8's place, and the 16's place. So this is saying, okay, it's 16 plus 8 plus 1, which is, dun dun dun, 25. Yay, we did it. Okay, so that is binary. Converting from binary to decimal, converting from decimal to binary, you are now pros. Okay, isn't that fun? So you can represent anything, any number, any piece of information, whatever you want, you can represent it in binary as just one big, long number. Assuming you come up with some system for representing things that everybody agrees on, but that's the hard part. You are professionals now. So what I would like to do, second to last for these slides, is to show you how to add binary numbers. Okay, so it's all the same. It's all exactly the same as adding decimal numbers. It's just you carry sooner because you have fewer digits. Yeah, so here is 1101 binary plus 1111 binary. Let's do this. Okay, let's figure this out. All right, how do we do it? So it's just normal as in math that we've learned how to do. So this is 1 plus 1 in binary. That's 2 in binary, which is 1, 0. Yes? So we have to carry a 1 finally. 1 plus 1 is 1, 0 in binary. Remember that. Okay, so the last digit is a 0. And so now we have 1 plus 0 plus 1. Again, that's 2, so 1, 0. Carry the 1. 1 plus 1 plus 1, that's 3, or 1, 1. Carry the 1. 1 plus 1 plus 1, that's 1, 1 again, and bam, that's our answer. Okay, it's all the same, you just carry a lot sooner, yeah? It might be easier for you, in fact. So this is the 0s, 1s, 2s, 4s, 8s, and 16s place. So this is saying that this number down here at the bottom is, let's see, dun dun dun, 28, yeah, cool. This is 28, and so this is all the same. All these numbers, that's 15, we know that, plus 15 minus 2, which is 13. Yeah, so this is all the same, and the math checks out. Okay, so that's how you add binary numbers. Not too bad, I hope. And then finally for these slides, I just want to show you something cool, but not really get into it. If you stay with computer science, you will eventually learn how cool this really is, but I just want to give you a taste. So I told you that computers are just a bunch of circuits, and we talked about them. So how do they actually do work? How does my computer use all of this information to do real work and, like, I don't know, do math? So I'm going to show you a circuit to add numbers. And the idea is, let's consider binary addition, yeah? So you got your 1 plus 1, well, it's 1, 0, 1 plus 0 is 1, 0 plus 1 is 1, 0 plus 0 is 0. Well, it just so happens that we have a logical operation that does addition. Ooh, what? What is this? So the exclusive OR, XOR operation, is doing 1-bit addition. 1 plus 1, yeah, it's 0 if you drop the carry. All of these check out. And you can combine a bunch of these, in fact, to compute any answer. And so yeah, this is how this works. You just give it two numbers, and XOR will add them to you if they're 1 bit long. And you can chain a bunch of XORs along by carrying things. So if A and B were both 1, well, then you carry. Ooh, then you have to carry a 1. In every other case, you didn't have to. And so you can chain along carries and feed those into the next exclusive OR to do the next adding. And so yeah, it's just a bunch of ands and exclusive ORs, and you'll have to consider the carry for every other digit. Okay, so you can chain a bunch of these adders together, and you can make a circuit that adds any size number you want. You just have to add enough of them. And your computers these days like to have 64-bit adders. Okay, so it's just a bunch of those XORs chained along to do all this addition. Isn't that fun? So that, I hope, has blown your minds, and that is the end of these slides. I would now like to switch gears to more of a philosophical topic again, and we're going to talk about privacy and encryption, and then you'll have a new essay this week. Okay, so let us begin. So we have, as a race, I guess, we've been talking about privacy forever. We've made safes, we have physical things that we want to keep private, yes? Well, now, in the digital age, we have digital things that we would also hope to keep private. And, well, how do we do any of this on the internet? How do we keep our privacy? Do we even have privacy? What does our government say about this? So, let's talk about the Fourth Amendment. Okay, so you may have learned about this once upon a time, and, well, what it does is it prohibits unreasonable searches and seizures. So that seems kind of privacy related, and, oops, the idea is, nobody, the cops can't bust in on you without a warrant, right? They need a warrant and probable cause. That is the hope, okay? And that's your house, though. The internet is not your house. It is a much different kind of place, and everybody's sharing information all over the little internet tubes. So how does privacy work there? So let's figure this out. We can use prior case law to think about how the law sees this as well. Let's talk about phones. So back in the day, the Supreme Court ruled that you didn't need a warrant to tap a phone because, these wires are going out of your house, right? And you cannot touch a conversation. It's not tangible, then it's not covered under the Fourth Amendment, they thought. And they changed their mind in the 60s. Now you do need a warrant to tap a phone. Okay, so that's the idea. The Fourth Amendment has been trying to protect you. All right? But are you protected is the real question. Okay, so you might read about this in the book if you bought it. It's a very fun little idea. Utilitarians, excuse me. So let's talk about the Target data mining. I guess you can call it a scandal, kind of. Well, what's the idea? What were they doing? And data mining, if you haven't heard that term before, it just means you're looking for patterns in data. So it's more like pattern finding. Okay, so think of it that way. So the idea is, it's really fun to think about how you can use data mining to do stuff like this. Pregnant women, they like to buy certain products. I think that's an obvious thing. And they like to buy those products at certain stages of pregnancy, okay? And Target noticed that, and they used that to their advantage, okay? So what they did is they took that data and rolled with it. They sent targeted ads, which is the most beautiful pun in this set of slides, probably this entire class. Targeted coupons and ads to those women, okay? And the question is, does that infringe on their privacy? Dun dun dun. So what does this mean? They were taking data about these people's purchases and using that to hopefully get them to spend more money. Does that infringe on their privacy? Were the things that they bought online or in the store with their card private? Okay? And so we can ask Kant, we can ask the utilitarians. Okay, now it just doesn't know what it's talking about. Okay, so Kant would ask, well, should everyone always do this? Do we have a right to look at people's purchases all the time? And I think you can imagine that Kant is probably all about privacy. Okay, he would probably say no to this. No, you shouldn't always have this information. That's probably a bad thing. Because then maybe you could do something horrible to me. Who knows? And then the utilitarians would ask, well, is there utility in this? For Target, yes. Yes, they're winning, right? If you were thinking about this from Target's point of view, yes, they can potentially make more money by mining this data about pregnant women and giving them targeted ads to things they might want to buy. Okay? And then they're also getting coupons out of the deal, so if they were going to buy it anyway, then maybe this is the best for everybody. Or maybe they didn't want to spend that money, and again, like we should go to no from their perspective. Okay, so it's an argument that you could make in either direction. I think Kant is pretty set in his ways, but utilitarians, you would have to argue, where's the greater utility? Okay, so that's the target data mining kind of scandal. That's one thing. Let's now talk about more things. So that's privacy, like with your credit cards, with your internet purchases. Let's talk about privacy on social media. So there's this thing called the right to be forgotten that exists in the European Union. So that's what the EU stands for, if you haven't seen that before. So they have this idea called the right to be forgotten. So would it be nice if I could delete all my horrible, cringy things that I posted on Facebook in high school? And maybe I can, but it's very hard to do. Okay, so Facebook, the last time I checked at least, it makes you jump through a million hoops to just permanently delete your account. It's easy to like take a little break, but you can still have your account and log back into it and people can still see your stuff. It's all kind of jumbled and not very fun. So, yeah, what the European Union does is they allow its citizens to demand that this data that's stored about them, to demand that it be erased. Okay, so let's talk about Google now. For example, Google lets you take links to articles about you, so these articles were about those people, out of their results. Ooh, that's interesting. So even if they did something stupid, and they were like the butt of a joke in the news, they can still get rid of, like, take their names out of it. Okay, they can be forgotten. So I guess the real question is now, and I would have you get into groups and talk about this, is does this infringe on our right to information that has been made public? Like, okay, this exists on a news site. If I just search for it there, I would find it. But Google's saying, okay, if you don't want to be in our search results, that's fine. I'm going to allow you to be forgotten from those search results. Okay, so there's this, I guess there's a question. You have your personal stuff. You have all of that, and that's fighting for recognition with this other large box, which is public good. Maybe this story is very newsworthy and important, and it would be very useful for Google to keep it on its search results. But this law allows you to, for your own benefit, get rid of it. Okay, so there's this kind of tug of war between all of your personal information and the public good, and I think Kant would think one thing, utilitarians might think another. That's the idea. So there's no right answer. I just want to show you all of these problems or topics that exist and have you formulate an opinion on them. Okay? So that's going to essentially be your next essay. You will form an opinion on a privacy-related topic. Okay, now let's talk about video surveillance. Because we've gotten good with machine learning. We can now recognize faces quite well. All right, so let us talk about driving. So you can, you used to be able to have these speeding ticket cameras in California, okay? But they eventually overturned them because they are not legal. They are considered to be what's known as a speed trap, and there is a law in California against those, okay? So we don't like that, and that is good, I guess, in my opinion. Less tickets for us, right? Not everybody thinks the same, though. France loves their speeding cameras, okay? They have them all over the place. So now there is, again, a line in the sand. So who has the right answer here? Who's doing it right? I guess California is more about personal information privacy. So this, like you in your car, they're taking pictures of you, of your license plate and things. That's personal information. Personal info that's being gathered, captured without your consent. And we're like, no, we don't like that. It's a speed trap. And on top of that, it's got this problem, then France, they're probably arguing it from a different perspective. They're like, okay, if we put speeding cameras everywhere, people are going to slow down, and that will increase safety. Yeah, so that's again, the tug of war that they're playing. There is no right answer, and different governments and municipalities and states, they all think different ways. So now let's get to something juicy. So Super Bowl 2001, and this was before 9/11, this was in February, they tested out face recognition cameras to check whether the fans that were attending the Super Bowl had warrants out for them, which is weird, interesting, I guess makes sense, kind of. They reportedly identified 19 people, 19 ticket scalpers and pickpockets, okay? And they were using video surveillance and face recognition technology to do this. And I'm sure you can imagine that 20 years later, we're a lot better at it too. So the ACLU was furious about this once they found out. And yeah, this is again a question of, okay, should we give up some privacy for this protection, or this so-called protection? I don't think a whole lot of bad stuff was happening with ticket scalpers, but maybe the pickpockets, we caught them before they could pick someone's pocket, maybe. So again, it's a bit of a gray area. Is this okay? And maybe our society is leaning towards, yes, it is, or no, it's not. It all depends. Okay? So all these questions, not a lot of answers, but hopefully you're coming up with some answers. What do you believe? That's all I want. That's all I want out of this class, is for you to determine what you think and argue it well. Okay. Let's talk about the internet some more now. So I'm sure you have been on a website or watched a YouTube video with ads. It's no fun. So I encourage you to use uBlock. I strongly believe in ad blockers, because they will actually even block the ads on your YouTube videos. So it's wonderful. So it's not illegal to block ads, but it is technically illegal to block ad blocker detectors on websites, which are sometimes built into ad blockers themselves, which is weird to think about. So it's like they go, have you ever gone to a website and it's like, you are using an ad blocker, you should turn it off. So it is technically illegal for your ad blocker to block that detection, the detection of itself, okay? Which is weird, I know. So the reason that that is illegal is because you're tampering with a certain kind of access control. And these websites, they're allowed to have access control. They have a right to control access to the copyrighted content that they are likely displaying to you. Okay, so that is a little bit of a gray area again. So let's ask our boys what they think. So should we always be using? Should we use ad blockers? And maybe you can frame this question and should we always look at or click on ads? Like, should we always buy the products that are offered to us? Because that's the point of ads, right? Isn't it? And Kant would be a hard no on this subject. Be like, no, I'm not required to give up all of my money to every ad that I ever see. That's silly. So I should just be allowed to block them because I'm not going to look at them or use them anyway. And then Mill, a utilitarian, would probably think about the benefits. What is the utility of all this stuff? So for one side, for the user side, you would maybe have fewer pop-ups, like fewer little ads that make your life a whole lot worse on the internet. Fewer pop-up ads, which we all hate, and there's more real content now. I don't have to like train my eye to figure out what is real, what is just an ad. An ad blocker would really help in that case. So that is probably the user's side. They would all be for ad blockers. And then maybe the website side would be against ad blockers, and it would be your job to reconcile between these two groups and figure out which one has the greater utility, so that you can make your choice as a utilitarian. The website that is probably using ads to generate revenue would make a whole lot less money if everybody used an ad blocker. So maybe it's a good idea to get rid of them because of that, because some websites are not like super large and they rely on ad revenue to stay afloat. So maybe that is something. And if that is the case, And a nice counter argument to that would maybe be that you can disable your ad blocker on certain websites that you support. So maybe it's a win-win in either case. But it's again up to you to argue, and argue well as a utilitarian. Okay, one last example about this privacy stuff. Let us talk about Google Street View. Okay, this is a little map. If you see blue, it's like, here are all the little tiny streets that have Google Street View on them. And then there's a huge gap in Germany. Okay, so pretty much all of Europe has Google Street View, and I mean, if they can totally get the cars into Germany, but there is a law. There's a law against taking Street View in most cities. Maybe the big cities they allow it, but the smaller ones do not. So Google Street View exists in all the streets, usually, in Europe, except for in Germany. Why? And I guess the question, or the answer, comes down to the culture of Germany. So culturally, Germans are a bit more mindful of their privacy. That's all. And the laws that they made there will reflect that. They don't care about being able to see, okay, yes, I know exactly what the outside of this place is going to look like, and it's going to help me get there. No, they'd rather make it so that, no, I don't want anybody to see my house, and that's that. No Street View for me, please. So, again, that's another tug of war between public good. Should we have this? They're taking pictures of our houses and our cars and us walking our dogs. Versus, no, I don't want anybody to see any of that, ever. There's two sides of that coin, okay? And I guess as Americans, we have also embraced Google Street View. I know I do, but not everybody thinks the same way, is the idea. Okay, so that is a lot of privacy stuff. And now let's talk about how we keep private stuff private. Let's talk about encryption, okay? So that is a fun concept, and I'm going to give you the basics of encryption now. So what encryption is, it's the process of encoding information, which is maybe a word that you, again, haven't seen before. It's just garbling it up, garbling some message up, so that only you and the sender, or sometimes only you and the receiver, and sometimes only the receiver, can decode that message and get it back and understand what you're actually saying, okay? So even if you announce your message to the world, if it was encrypted, only the person that it was intended for, only the parties that it was intended, that were intended to receive it, are able to decode that message and actually understand you. Otherwise, it would just look like a garbled mess. And that is useful on the internet because you're logging into your bank, maybe. You're logging into your bank, and maybe you're making purchases online, like you're buying something on Amazon, and you're entering in your credit card. All of this stuff you do not want anybody else to see. Decode also means decrypt. You might see that word as well. I might say that word as well. We would like to encrypt all of our information that we're sending across the internet and stuff that's sent to us in the hope that nobody else will see it. Okay? So the idea is encryption makes sure that your credit card number only goes to Amazon, it only gets sent to them, even though it's traveling through Comcast's internet pipes. They rebranded, called themselves Xfinity, but they're still Comcast and horrible. That is the idea. Okay, so they can't tell what you're doing. They can tell that, okay, you're talking to Amazon, you're sending some message. They have no clue what the message says, and that's beautiful. That is what we want, I think. Okay, so let's talk about how to encrypt something. Here is the simplest form of encryption, and it's called the Caesar Cipher, or ROT13 is how I will pronounce this. And the ROT stands for rotate. All right, and here's how you encrypt something using the Caesar Cipher, using ROT13. You just take a letter, like A, and you shift it 13 letters through the alphabet. So A becomes N, and B becomes O. That's 13 letters later, yeah? So that's the idea. So A plus 13, that's N. And the reason people like the 13 is that the encryption is its own inverse, because decrypting n goes back to A because you just wrap around. So that's why they chose the 13, because we have 26 letters in the alphabet. It's half. It's beautiful. So if you go back, if you do the same thing again, you get back to the original message. Okay, so that's the Caesar cipher, if you haven't heard of that. You can do like rot 5 or something. That's just rotating at 5 characters, but the inverse is not the same anymore. You have to go back 5 characters now. Okay, so that's the world's simplest encryption scheme, and maybe it was popular around Caesar's time or something. So hello, if you're going to encrypt that, you take the H, be like, okay, the H is the U, the E is the R, all that stuff. So hello becomes Uryib, and then you can use the same process again to go back. Okay? From Uryib to hello. So that is rot 13, the Caesar cipher. Obviously, it's completely broken now, because if you send this message to anybody, they're like, okay, yeah, that's probably rot 13. Let's just check really quick. And yes, this looks like English again, so we were right. So you don't want to send anybody stuff using the Caesar cipher, and that's definitely not what you're sending to Amazon. All right, so let's talk now about advanced encryption. And a very nice advanced encryption scheme is called RSA. It stands for three people's names, their last names, the people who invented this in the 70s. And it's actually so secure that it's still used today. It's most likely going to never be breakable, assuming you keep the numbers large as computers get faster. So here's the idea. When you're encrypting something, sometimes there is some concept of a key. So like, here's my best drawing of a key, and you use that with the message that you're sending to somebody. So that plus a key will give you back the original message. Okay, it's like that's the original message or something. So in RSA, you have what's known as a public key. The key to encryption is publicly available, out in the open for anybody to see, and they can send you a message using the public key that you're showing to everybody. Okay, so here is you. Here's you who wants to receive something, and here's the sender. You are sending across to everybody your public key. So the sender can see that, and they have this little message that they want to send to you. And on the flip side of a public key is what's known as a private key. And that, coupled with the public key, is what lets you decrypt messages that are sent to you. So the sender takes your public key and encrypts their message with that key. And you, over here, you have your private key. Whee. That can decrypt any message signed with your public key. That is the idea. Okay, so it's like a lock that takes 2 keys to open is the idea, and you only give one person your key, and that's enough to send the message, but to decode the message again, you need that private key back. Okay, so yeah, that is the idea. There is this secret private key that lets you decrypt messages sent to you, and the keys, all this stuff, they're just numbers. So RSA works because it's really hard to factor those numbers, and it is most likely going to never be easy to do that. Quantum computers make it slightly easier, but then you can just use giant numbers. That's the idea. Only if p equals np, if you've heard that problem before, will that ever become easy. Okay, so let me show you very quickly how to do RSA. I don't expect you to understand it. I'm not going to ask you on a test to do this encryption, but I just want to show you how it works because it's really cool to think about. So your public key is a pair of numbers. We say N and E in the literature, and your private key is called D, and those are all generated from 2 huge prime numbers, hopefully. I made small numbers, but you can imagine that they get giant. So yeah, that's the idea. And D and E, they are known as modular multiplicative inverses, which you do not have to understand unless eventually you take CSCI 26 with me, which is several semesters later. That is a very interesting concept, and just take my word for it for now. That's a really cool thing. And this allows you now to send any message you want call it m, between, your message also has to be a number, between 0 and n minus 1. So I can send any message between 0 and 3232. Okay? So 0 and 1 don't really work right, so you usually pad your messages and you don't ever choose 0 and 1. This is not exactly what happens in the real world, but it's a very good approximation. So let's say we have a message, and we want to encrypt that message. Okay? So we'll say, we'll calculate m to the e mod n. Okay? And that mod is this operator again. Yeah? So that is our encrypted message. And then to decrypt our message, we calculate c to the d mod n. Okay? This will give you back the original m. So that is RSA in a nutshell. I don't expect you to understand a lot of it, but it's just a cool thing. Oh, and before we go, in case you're wondering about what this means, modular multiplicative inverses, it's saying that m e to the d, like they kind of cancel each other out. That's essentially what you're doing down here. So m e to the d equals m when you take remainders by n. Okay, so that's enough words. That is the example. Let me show this to you very quickly. Let's pick our favorite message. I don't know. Let's say that our message is 42. So I'm going to use Python, which we're going to learn eventually in this class. Don't worry, to do all this encryption just to show you how cool it is. And then we'll go from there. So here's my m. M equals 42. So now when I say m, it's just 42 is what I get back. So now I'm going to calculate my encrypted message. So I'm going to say m to the power of e mod n. Okay, m to the power of, yeah, I'll just type it. M to the power of 17, that's e, mod n, which is 3233. That's 2557 apparently. That is our c. And so c equals 25557. And now to decrypt c back to m again, we'll do c to the d mod n. So c to the d, which is 413, mod n, which was 3233. And what do you know? We get 42 back. So that's, in a nutshell, RSA. It works because of cool math, and yeah, that's encryption. That's what I want to show you there. And then finally, let's talk about the ethicality of all of this. Is it ethical to use encryption to send messages to other people? Like, should we be allowed to do this? And so let's ask our boys. Kant would probably say, like, we'd ask the question to Kant, hey, should you always be allowed, like, if you wanted to talk to somebody privately, should you always be allowed to do so? And I think that Kant is a proponent of privacy, and he would say, yeah, totally. If you don't want to share information with the entire world, that's totally fine. That's a normal thing to want. So Kant would say something like, yeah, private info should stay private. And then Mill would be like, okay, let's weigh this. Let's weigh these options. Privacy is a good thing. I think most people like that. You could argue that, okay, privacy is good, so therefore we should be able to use encryption. Or maybe you have like terrorists sending each other messages, and if it's encrypted, we could never understand what they're saying. So, and that is how some of the laws get made in this country. They use the terrorist route to make a law. So maybe if you want protection, we should not have this encryption. That's the idea. Maybe we should make backdoors for people to use. And there are unfortunately quite a few backdoors that a lot of companies give governments. And I am not a big fan of that, but there are definitely arguments for it. Okay. So, before we go, three slides and we're out of here. And that's time for your essay. So let me talk about 3 important, relatively recent topics, and you're going to write an essay on the last one. Okay? So let's talk about Chelsea Manning first. There's this site called WikiLeaks, which you may be familiar with. They like to release data that is usually classified, confidential, but somebody leaks it to them, and the whole world can see it. Okay? So, in 2010, Chelsea Manning, she gave WikiLeaks quite a few classified or sensitive documents that were about the military, about diplomatic things, and it was huge. It was a huge leak. It was showing a lot of things like civilians being killed in like the Iraq War, if I remember correctly, and that was information that we did not know about before, and that was quite sad. And so this happened, okay? And I think you can imagine that this is quite impossible before the digital age. This would never have happened before. It's so difficult to get that many things out to somebody else. Okay? And so what happened she was sentenced to prison for this leak because it's not a good idea to give away these things. There are laws against it. A lot of people say it, even though the information was very, I would say it was useful to get to the public, right? So sentenced to 35 years in prison for this, and it was that sentence was commuted by Obama in, I think, the final parts of his administration. So I guess the question now that I want to pose to you is, does the value of informing the public when like bad things are happening done by like either governments or militaries that belong to governments, does that outweigh the value of confidentiality? And again, there are two sides to this coin, as there always are. You could say that confidentiality protects people. And that was the argument. That was why she got such a sentence. It was because, okay, these top secret documents, they had people's names on them. And that was kind of WikiLeaks' fault for not, well, there were too many to actually go and scrub out everybody's name, I guess, was their argument. But now I'm just waffling on. So confidentiality protects people. So that's one side of the coin. Like, this all had people's names in it, and they could like be the target of some angry mob now because all this information is now public. But all this information was very useful for voters and activists, I would say. You would get more info if you were allowed to leak this stuff. Because if they saw like what was happening during the war, maybe they would vote against it or vote for a different president, things like that. And then everybody wants to make sure that no crimes are being committed. That's the idea. So again, there are two sides to this coin, and it's your job to argue which side you're on. That is all. There's no right answer. Okay, so that's Chelsea Manning. Let's now talk about another huge leak, the Panama Papers. So there was, once upon a time, a hacker took not just a few 100,000, but millions of documents, and this was from a law firm in Panama. And the documents, they showed how that firm made helped make offshore companies for foreigners, okay, so people who didn't actually live in Panama, for the purposes of usually investing a lot of money. And people thought that most of that money was corrupt, okay? So it was easy to get your money in Panama and then use that to invest, and it was wiped clean of all of its crimes, okay? So people thought that this was all corrupt, and a lot of people, like, this released a lot of people's names. Like, here is a map with every country colored in if that country had people who were implicated by these papers, okay? That is the idea. And so on one side, it's like, yes, we need this information out there because these people are corrupt and we should take this money away from them. We don't like that. On the other hand, a lot of people implicated were just following the law in their country. Even though it was shady to like make an offshore company, put your money somewhere else, it was probably for the taxes, fewer taxes to spend on this, on your capital gains or whatever. That's the other side of the coin. A lot of people were following the law. It was the law's fault if they were allowed to do this, not theirs. They shouldn't be the target of an angry mob. They were just trying to make money, right? Everybody needs money. So you have this side versus this side again. Which side are you on? What do you think? And I'll be asking you this in your essay. So again, this leak is gigantic, and I think you can imagine that there's no way that this would have happened before we were allowed to put stuff on the internet and everybody was interconnected with their computers. Okay. The final topic for this lecture, then we're out of here. We'll talk about your essay and get out of here, is Edward Snowden. So he was a contractor for the NSA, National Security Agency, and he leaked documents in 2013, so relatively recently, showing how the NSA was spying on its citizens and others. Okay? And they had a lot of backdoors in popular services like Facebook and things that were thought previously to be completely encrypted. Like my information is not being shared with anyone right now because I thought that this was all encrypted, but it was not. And so this was all highly, highly classified. Let me say that. All of it was classified. So the NSA, though, was breaking the law. They were not allowed to do this, given the laws at the time. They captured a bunch of information that it was not legally allowed to capture. Okay? So Snowden was indicted for espionage. That was how they charged him for leaking all these classified documents, because obviously there are laws against leaking such things. And he's currently living in Russia with his wife to avoid prosecution. So that is a mouthful. That is a lot going on for this one man. And he leaked classified things, but on the other hand, they showed that the NSA was doing bad stuff. What do you think? And so now it's my turn to finally ask you what you think as a non-rhetorical question. So let me pull up your essay assignment and then we'll be done. All right, I am back. Let us go. Here is your essay. I guess it'll look like this for you. This is a 500-word essay, and what I would like for you is to talk about the topic of Edward Snowden. So I want you to respond to this prompt in 500 words. Was it right for Snowden to blow the whistle? He was a whistleblower, we call him, on the NSA. Do we have a right to privacy on a public utility like the internet? After all, like PG&E, it's monitoring my energy usage, and nobody really cares about that. The NSA was just monitoring internet usage, right? Was that really a bad thing? So respond to this prompt in 500 words, and yeah, that is the idea. It doesn't matter which stance you take. You'd be like, okay, yes, it was a good idea. No, it's a bad idea. You don't have to have a stance. You could be like, okay, it was good that he did this, but it was bad for this reason as well, so I'm kind of in between, as long as you argue your points well. Okay, you just have to always remember to mention both sides of the argument and argue in favor of or against them. So I want you to formulate a coherent argument. Okay, I want to understand you, whichever stance you take or lack of one. I want to understand why. Okay, and I want you to talk about that. You're not required to talk about in this essay Kantianism or utilitarianism, but you might find it useful. And there is a citation requirement now, though. Okay, I want you to cite at least one source in your essay. Okay, so yeah, that is your next essay. It's only 500 words, and yeah, everything is the same as before, so I don't care how you format it. As long as you show I can read it and understand the citation that you make. You are required to cite one source, remember. I think that's everything then. So good luck with this. Please yell at me if you have any questions, and I will see you in the programming lecture.